Well, this is a rather troubling slide because here they tell you that if you happen to have the formation of a carbocation intermediate, let's say that you have this terbutyl chloride, and so there you have a very good leaving group, right? Or a decent leaving group at least. The chloride may leave, and you will form a carbocation intermediate, right? And that is going to be a tertiary carbocation. Tertiary carbocation. But how about if, because of the ratio of ethanol water that you have there, which is not indicated, how about if the E1 is not as favored as you would like? So chances will be that even before the chlorine leaves, something else could happen, right? And you can have CH2H, CH3, CH3, and then the water molecule that can behave as a base there. It can help you to remove one proton. You form a double bond here, and simultaneously the chlorine leaves. So what kind of mechanism is that? Well, so that will be the E2. And because those hydrogen atoms attached to the CH3s in the starting material are very accessible, so that will be a possible scenario. So you will have some possibility of competition with an E2, depending on the ratio of ethanol water. If the concentration of water was high enough to favor strongly the formation of a carbocation intermediate, so there you will form this carbocation that later on you can have the base water that will abstract the proton, and that's why we will call that an E1 mechanism, right? So that will give you that product, right? And because first we formed the carbocation intermediate, and then in a second step, water came and abstracted the proton to form the final product. And you have yet one other possible competition, and that is the possibility of an SN1. Every single time that you form a carbocation intermediate, you will have the possibility that the water molecule, instead of behaving as a base, it can behave as a nucleophile, and that will give you this product, right? That will give you that. And all what it takes to go from here to there is just the removal of one of those protons. Another water molecule can help you to do that, right? Another water molecule. And there you get substitution. And so that would have been an SN1. So that is a big mess, right? You have this terbutyl chloride, and it can go E2, E1, SN1. So you have quite a number of possible paths. Well, and then we have this slide. This slide here is quite interesting. I like the discussion associated with this particular slide. So here we have the same compound, methyl chloride, in two different chair conformations. So you tell me, which one of these chair conformations, left or right, which one is suitable for an E2 elimination? Think about the requirement of antiperiplanar relationship between the chlorine and the hydrogen that is going to be abstracted. So here I have a chlorine that is antiperiplanar to that hydrogen, but not to that one, not to the other in the back there. And then in the other structure, is the chlorine antiperiplanar to any hydrogen? No, it cannot be, right? Because here the chlorine is on an equatorial position. Being equatorial, the only thing that is antiperiplanar to that chlorine is a carbon-carbon bond there, right? So that is not good for E2 elimination. So the only one out of the two possible conformations, left or right, is only this on the left that can go through an E2. So I will have the base, abstracting the proton, forming the double bond, and then getting the chlorine departing, all that simultaneously, right? So which will be the best conditions for an E2 elimination in terms of the strength of the base? The preferred conditions are a strong base. So that's why here we are using 1 molar sodium ethoxide. 1 molar sodium ethoxide. So it's a rather concentrated base. And a more concentrated base, well, that is going to increase the chances that the base will abstract the proton that you want, right? So, in the meantime, the conformation on the right, does it mean that the conformation on the right cannot experience any elimination? No. It is possible that you can still go through an elimination reaction, but instead of being E2, it will have to be E1. And what does it mean, the E1? It means that first the chlorine will depart, the chlorine graciously will leave, and it will form a carbocation intermediate, right? So the chlorine is gone, and you will form a carbocation. So the chlorine is gone, and you will have a carbocation there. And then now, the E1 mechanism, it doesn't have the requirement of antiperiplanar, right? So you can abstract the proton on the left, or you can abstract the proton on the right. Both of them will be suitable. So which one would you prefer to abstract? The one on the left or the one on the right? Well, I would prefer to abstract the one that will give me the more highly substituted alkene, right? So I would prefer to abstract this one on the right because that is going to give me this product that is more highly substituted. I can abstract the other as well, right? But the other one will give me a di-substituted alkene, so it's not so appealing. In the case of the E2 elimination, I was forced to abstract that proton because, well, I didn't have any other option because there was the requirement of antiperiplanar, right? Now, as far as the concentration of the base, so which one will be a good concentration of base if you want to perform an E1 elimination? Well, because the E1 requires departure of the leaving group first. So you may want to have a weaker base, or you may want to have simply a dilute base, right? That's why we are using 0.01 molar sodium ethoxide. And in that way, that will give time for the chlorine to depart. And then only then, the base will abstract the proton from the neighboring carbon. And so that is quite an interesting pair of reactions. And let me see what else we have here. Yes. So and then the next kind of elimination reaction we have is the one that we call E1CB. E1CB is a conjugate base. So here, in some way, this is like the opposite to the E1, the simple E1, because here we have abstraction of a proton instead of in the E1, it was first departure of the leaving group. Here now, here is the base abstracts the proton and generates a carbon ion. A carbon ion. You have a negative charge there. In order to have a relatively stable carbon ion, it will be desirable to have some functional group close by, like the carbonyl group there. That will help you to stabilize that carbon ion. You can have other groups also, like a nitrile. A nitrile could do the same job, right? A good job. And then here you have two resonance structures for that carbon ion. And then from either one of the two resonance structures, starting from this one or from the left one or the right one, you can regenerate the carbonyl group, regeneration of the carbonyl group, bring back the pair of electrons here, and then push out the leaving group. And that will give you your elimination product. Example of this kind of elimination in nature, well, we have that in this particular reaction. Here we have a thioester because of the functional group here. And because we have a carbonyl group that is right next to the carbon atom from where we are abstracting the proton, so there we have a carbonyl group that may help us to stabilize that negative charge. And then once we regenerate the carbonyl group, bring back the pair of electrons here, then we can eject an OH. So there you will say, ejection of an OH is such a bad leaving group. Yeah, but if there is a proton that is waiting for that, so that will form water, and that will make it a better leaving group. So and there we have formation of the crotonyl thioester. So in the next mini video, we will get to see the competition of all different possible mechanisms, and we will analyze some particular reactions to classify them as E1, E2, SN1, SN2, etc.